This is the third of 4 videos looking at P3 Particle Model of Matter from the AQA Physics syllabus. Now each time I've used this mind map here to focus ideas. In the previous 2 videos we've looked at density and the states of matter with internal energy. In this one we'll be looking at latent heat and specific heat capacity. So your syllabus states that if the temperature of a system increases, the increase in temperature will depend on the mass of the substance heated, the type of material, and the energy input to the system. You've got an equation, which is the change in thermal energy equals the mass multiplied by the specific heat capacity multiplied by the temperature change. You've got the definition: the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So to put that in other words, if we heat some solid, its temperature will rise, and the amount the temperature goes up will depend on 3 things. First of all, the amount of energy that you've transferred to the solid. Secondly, the mass of the solid, that'd be how many kilograms it is. And thirdly, the type of solid. So thinking about the type of solid, if we transfer the same amount of energy to a kilogram of different solids, they actually heat up different amounts. So as an example here, if we transfer 1,000 joules of energy to a kilogram of lead, its temperature will go up by 8 degrees Celsius. But if you add the same amount of energy to a kilogram of copper, its temperature will only rise by 2.5 degrees Celsius. And what we say is it means that copper has got a higher specific heat capacity than lead because it takes more energy to heat the copper by 1 degree than to heat lead by 1 degree. Now, specific heat capacity has got a definition which you've got to learn. It's the amount of energy required to raise the temperature of 1 kilogram of something by 1 degree Celsius. So try and memorize that one. It's an easy mark or couple of marks. Now you are given the equation for specific heat capacity on a formula sheet that comes with your exam. So you don't have to learn this, but you do have to be able to use it. One of the aspects of using it is we have to know the units that everything is in. So your energy has got to be in joules, and in the equation that's given as a triangle, then an E. The triangle simply means change. It's the Greek letter D, delta, and it's used in maths and science for the change in something. Mass has got to be in kilograms. The temperature change, which again is using this Greek letter delta, and then the Greek letter TH, theta. So we say delta theta. That's got to be in degrees Celsius. And as long as you've done all of that, your specific heat capacity will be in joules per kilogram per degree Celsius. Written J stroke kg degree C. Right, and again, it's come up in the past. What is the units for specific heat capacity? That is it. Try and learn that. So moving on now to latent heat. The syllabus states that if a change of state happens, the energy needed for a substance to change state is called latent heat. When a change of state occurs, the energy supplied changes the energy stored, that's the internal energy, but not the temperature. The specific latent heat of a substance is the amount of energy required to change the state of 1 kilogram of the substance with no change of temperature. The specific latent heat of fusion is the change of state from solid to liquid, And specific latent heat of vaporization is the amount of energy it takes to change the state of 1 kilogram of a liquid to vapor. So putting that in other words, if we take some ice at 0 degrees Celsius, it would change its state to water, but not its temperature. Energy must be transferred from the environment to change its state. And that amount of energy is called the latent heat. So the latent heat is the amount of energy required to change the state of something. So that was latent heat. Now sticking the word specific before the word latent heat simply makes it specific to 1 kilogram. So our definition is the specific latent heat is how much energy needs to be transferred to change the state of 1 kilogram of something. And we have two versions of specific latent heat. So if we're going from solid to liquid, that's melting, that is called the specific latent heat of fusion. So that would be the amount of energy required to change 1 kilogram of a solid to the liquid without changing its temperature. And the other one is the change from liquid to gas. So for that one we use the phrase specific latent heat of vaporization. So that would be the amount of energy required to change 1 kilogram of a liquid into gas without changing the temperature. Now in the exam you might be told that the specific latent heat of fusion of ice was 300,000 joules per kilogram and be asked, what does that actually mean? Well, you would write that that means that 300,000 joules of energy need to be transferred to a kilogram of ice at 0 degrees to change it to a kilogram of water at 0 degrees. Now it also means that 300,000 joules of energy would be transferred to the environment from a kilogram of water at 0 when it freezes to form a kilogram of ice at 0. And that point there is quite often missed by a lot of students. So these two, they match one another. Now two other important points we can draw out from this. First of all, this is a physical change, not a chemical change. Physical change, easily reversed. We're just rearranging the way the pattern of the molecules between being in a neat lattice of molecules in the solid and being in the random arrangement in water. So that's the first thing. Second thing is that this is an example of the conservation of mass, that you start with a kilogram of ice and end up with a kilogram of water. There's no mass gone anywhere else. It's still a kilogram, so you haven't lost substance. Law of conservation of mass. So now for the second one, the specific latent heat of vaporization. You might be told that the specific latent heat of vaporization of water is 2,260,000 joules per kilogram. What does that mean? Well, it means that 2,260,000 joules of energy need to be transferred to a kilogram of water at 100 to change it to a kilogram of steam at 100. It also means that 2,260,000 joules of energy is transferred to the environment when 1 kilogram of steam at 100 changes to 1 kilogram of water at 100. And this is important to know about from a practical reason, that if you stick your hand through a column of steam coming out your kettle, then that steam quickly condenses to water, and when it does so, that large amount of energy is transferred to the environment, and you have made the environment your hand. So all that energy is absorbed by your hand and results in a scald. So this is the specific latent heat equation, which states that the energy for a change of state equals the mass multiplied by the specific latent heat. The energy is in joules, the mass in kilograms, and therefore your specific latent heat is going to be in joules per kilogram. Now this equation is giving you on your equation sheet, which will be inside your exam when you do it. You don't have to learn it, but you do have to be able to manipulate it. And the most likely one is that you're going to have to find the latent heat when you're given the information about the energy and the mass. So you have to be able to rearrange that equation. So if you were asked how would you practically measure the latent heat of fusion of water, what we would set up is something like in the diagram here. So we have an experimental setup which has got a heater attached to a joule meter, which will then be attached to your power source. The heater is embedded in some ice placed in a funnel with a beaker underneath. You then have a control setup which is exactly the same, except the heater is not connected to the power source. Now both of those are going to melt, but the one labelled A, that's the experimental setup, that will melt more because it has got the heater in it and the heater is connected. So we are interested in the difference between what you get with A and B. So you turn the heater on in setup A, ice will melt and that will drip into beaker A. Some ice also melts in the control setup and that will drip into beaker B. So after a time you find the mass of both beakers of water and subtract them. And if you think about it, that gives you the mass of ice melted by the heater. The joule meter tells you how much energy has been supplied to the heater, so you've now got the energy and you've got the mass. You rearrange your equation to give latent heat is energy divided by mass, and that will give you your latent heat. Typical results there: if you melt 0.1 of a kilogram of ice, the energy transferred to the heater would be 30,000 joules, and then you do the rearranged equation to give you the latent heat of water from that. So finally we look at heating and cooling curves. The syllabus states that students should be able to interpret heating and cooling graphs that include changes of state. Now this is a heating graph. On the x-axis we have the time of heating per second, and on the y-axis we have the temperature. Now it's important to realise that as long as you're supplying the energy at a constant rate, in other words you've got a steady power input, then the time of heating could equally well be written the energy supplied. That's important to realise that. So you may get a graph in your exam with energy on that axis. Okay, reading the diagram then from left to right, you start off with the solid, you supply energy to the solid and the solid gradually gets warmer. It then reaches its melting point. As soon as it gets to its melting point you supply more energy, and this is now your latent heat, and the temperature doesn't change, but the object changes state from solid to liquid. When it's all changed into liquid, further energy supplied will cause that liquid to warm up, in other words to change its temperature again, until it reaches its boiling point, when the same sort of thing happens again. Energy is now supplied in order to boil the liquid, the temperature stays the same, and then once it's all boiled, it's now all gas, and then supplying extra energy to the gas will make the temperature of the gas go up. The cooling graph is exactly the same but in reverse. So you start with a gas in this one, It cools down, so this time we're transferring energy to the environment. When the gas reaches the boiling point, it will then condense. Further cooling will carry on that condensing process until it has all turned into a liquid, but the temperature doesn't change. Then the temperature will continue to fall in the liquid phase until it reaches the melting point, at which point it will start to freeze. And then the freezing process happens. You're continuing to transfer energy out of the liquid to the environment. It changes into a solid, and then beyond that the solid itself then cools down. So this would be the sort of thing that would happen if you took some steam and put it into an ice cold room, maybe with a temperature of -10, and then if you measure the temperatures there, that would be the profile you'd get as the states change from gas to liquid to solid.